Hello guys. Here's the lecture 5 and the section that we're gonna cover from section 4 to section 7. Sorry, this one is 7, not 4. And which basically the starting point where we stopped last time, or last example that we solved it, talking about the conservation of energy when I have a charge located or moving in electrical potentials, and we find the velocity or the charge or the electric potential based in the conservation of energy. So here's the conservation of energy. The initial energy, it should be equal to the final energy. That's the conservation of energy formula. What we have in energy in that case, I have kinetic energy and I have potential energy. Kinetic energy, we call it Ki plus potential energy, we call it U potential energy, and both of them, they are an initial. So Ki, which basically depend about the movement, Vi, which is the velocity, plus the potential energy, which basically is just the charge times velocity for electric potential. So I need to identify where is my initial energy locations, where is the final energy location. The starting point here is the initial locations. So this is my initial positions and the charges I, and here is my final locations. And here we have Vi equal, here is the 50 meter per second. And here is the V final, that what I am looking to find in this problem here. The reason why, here in the question, the ask you, is the charge moving faster or slower? So I have initial velocity. I need to find the final velocity to make a decision it's faster or less. So here is the Vi equals 0. So that's one lead me to eliminate this term here. So I end up with the EI, just basically a half here is the half times M. Where is the M15? Power to the minus 9 kilogram, or times minus 6 gram, and here is the times 1 kilogram per 1000 gram to change it to the kilogram, and we have Vi 50 meter per second, and this one is square, and this number you end up with the 1.88 times power to the minus 5. The unit, it is joule. So that's the unit for, or the initial energy. Now final energy, the same formula, except I don't have the final velocity yet. So I need to find it. Here is the M times V final square plus Q times V final, whereas the V final is 200 in that case here. Okay, so I can type it here is the a half M V final square times Q plus Q, which minus, don't forget the minus here, nano column. So this is the power to the minus 9 column times 200 volt, and then we're gonna use the EI equal EF. I have here is the 1.88 power to the minus 5 joule. That's equal a half M, it's just 15 power to the minus 9 kilogram, minus 9 kilogram. Sorry, it's my pointer acting up. V final square, I don't have that formula. And here is the minus, because here comes from here, 2 power to the minus 6. This one is joule. So from this formula here, we can find V final and up with the 53 meter per second. So in this case, I have 53. I have initial velocity 50. So that's obvious. My charge or the charge in that situations will be faster than initial charge by 3 meter per second. That's the first example. Now the second concept, when we're talking about this one specifically, we're talking about the capacitor inside two plate capacitors and the relation between electric potentials and electrical field depend about some parameters regarding for the capacitors. For example, the charges located in two plates and the cross sections area for the plates and the distance between the plates. We call here is X or D. Okay, so those combination of the parameters, that's how to govern or control the relation between potential volt or electric potential and electrical field. So you can find any one based in what you have. Okay, let's see what you have here. Beside this one, your textbook mentioned about when we have the case a charge or point charge located or pointed in a sphere surface. In that case, the potential voltage, it has a specific formula. It needs to be applied, K, Q times I. So the charge that's distributed in the sphere and the R, the radius of the sphere. And here's some comment. You look at this one. And the mainly comment here when you're talking about all some of our electric potentials depend about the Q, not absolute value of Q. Means the electric potential could be negative, could be positive. And that one lead us to confirm that the electric potential is just number, not vector. So this one is a scalar. So in this point here, it's gonna be very useful when we have multiple points or multiple charges and we need to find the electric potential at certain point. We're gonna see in the second video how that that formula lead me to easy to find it electric potential. Now just reminder for the formula that we mentioned before. Here is we have two plates and the capacitors. And the first two questions ask you what's the field point. So basically, as we know, point from the positive charge to the negative charge. So this is the direction of the electrical field. The second one asks you to find the magnitude of the electrical field. This depended, as we mentioned the previous slide, depended about the electric potential between two plates. So here is the E capacitors, sometimes we call it E cap, E capacitors. Just in this case, from the positive side, VA minus VB divided by D, this distance. Or sometimes we can type it delta V, difference potentials, divided by the distance between two plates. As a unit, delta V, volt, delta or D is meter, volt, meter. And we know the original unit. So either way is you can use for electrical field unit. Now here's the numerical example for that. We have the two plates. They are separate with 2.5 centimeters and a cross sections area 0.75. And they put it between the electric potential 29 kilovolt. So we have A 29 kilovolt and the P 80. So if I wanted to identify my electrical field in between the capacitor plates, basically I will use delta V divided by D, whereas the delta V is 29 power to the 3 volt minus 0 volt divided by the distance. It should be using the meter unit, 225 meter. And this numerical value, it is 2 power to the 6 power to the, sorry, again, power to the 6. I can type volt per meters or Newton per coulomb. Okay. Now, the second question asks you what the charge in that situations when we have a 200-volt potential difference between two plates, how much charges we have. So we can find it with the formula is the Q divided by permittivity or absolute zero times the cross sections area. So I need to find the charge. So I have the cross sections area, permittivity is just constant. So I can find my Q, it's basically E times absolute address times A. I have all the information that we need. E is 1.2 power to the 6. I will use the Newton per coulomb as a unit, multiply by permittivity. It is 8.8 power to the minus 12 as a unit. This one is the unit is coulomb square divided by Newton meter square and multiply by cross sections area 0.75. Sorry to again 0.75 meter square, and now is my unit match. Cancel this one will cancel this one, and this one I end up with the 7.7 power to the minus 6 coulomb or 7.7 micro coulomb. That's the charges that I have between those two plates. The last part here as an introductory when we have multiple charges, and the formula is straightforward. When you have couple of charges that are distributed, then when you find the electric potentials, and the only formula that we use, we mentioned about is positive or negative, just added those components together. So this, since they are scalar, they are not vector, so we type the formula and write down the numbers. Now, according for these three cases, and they ask you to find electric potential in the dot one here, and that equals 0, algebraic addition. So here's the Q1 and Q2, they are positive. So this one not gonna lead me to the 0. One positive, one negative, so that's the only case lead me to the 0. A negative to the negative, you're gonna lead me to the negative electric potential, not 0. Okay. Now regarding for the representations, for to find the net force, net electrical field or net electrical potentials, if I have the situations two chargers located, let's call them is the A and B. Here is the A and here is the B. Similar for this one, here is the A and here is the B. And distributed here is the R1 and here is the R2. Now here is the electric field comes from the A, pointed that way. Here is the electrical field comes from the charge B, and the net electrical field will be 0 since the discharge pointed in the center. In electrical potential, that's the difference. So total or net, just basically straightforward. K QA divided by R, we call it R1. Here is I call it R2, sorry. Call it R2 plus QB, here is the K, sorry, divided by R1. If the R1 and the R2, they are equal, if R1 equal R2, I end up with the V total or V equivalent equal K divided by R QA plus QB. So that's the situations when we have electrical potential and electrical field. Okay, I will stop recording for this video and see you next video. Thank you.